Поставить, нужно показать, остановить трансляцию. Вот здесь вот есть какой-то звук, видишь? Да.
Так.
Наверное, должно быть слышно, раз в OBS есть.
Наверное, уже пора включить.
Сейчас я забыл, вот это нужно выключить, да, по-моему?
По-моему, да.
На правой доске не писать.
Да, все, трансляция есть.
И звук есть, да? Ну, супер. Да, только окно не открывается. So, we are starting the proof of existence. We are of Hilbert schemes. And as we argued last time, it follows from the existence of quad schemes. And as we argued last time, it follows from the existence. And just as a short reminder, the Hilbert scheme, it depends on, say, n and on some polynomial h, Hilbert polynomial. So it carries some universal subscheme. Maybe let me call it U, and it's a closed subscheme in the projective space. And it's a closed subscheme in. Okay, and all the fibers, well, so to say, the fibers, all the fibers of pi are all the subschemes of Pn with Hilbert polynomial H of R. Okay, so this is yes.
Pn начальник.
So say over our, we're going to work over our beloved algebraically closed field K. Okay, though when we prove this theorem, it will be proved in much bigger generality over arbitrary base scheme. But at least for the starter, we can consider this ground field K. Okay, so also pi is flat. Pi is flat. So it is a universal family, the universal family of all the possible subschemes with given Hilbert polynomial. Okay, and that's what we are trying to prove. But I explained last time that follows from the existence of quad scheme, and for the quad scheme we are given. Yes. No, by no means. How do you mean? If h is constant, then pi is finite. Otherwise, its relative dimension is equal to the degree of h. Yeah? Yes. What is U? It's the universal scheme over the Hilbert scheme. The Hilbert scheme parameterizes all possible subschemes in projective space with a given Hilbert polynomial. And now there's the universal family. The fibers give you all such subschemes and each exactly once. It's a moduli space of subschemes with this Hilbert polynomial. And this is the universal subscheme.
And it exists.
The theorem claims the existence of such thing, yes.
And universal means that any other family is a pullback.
Right. So we discussed this last time, so maybe I will not repeat this discussion.
The universal family was not discussed. We just discussed that this hill is representing object.
Yes, but it just means that there is a universal family, right? By the very definition. Any family is induced from this one, just by pullback. So if there is some other family, I don't know, T, then you just pull back. Okay, so, pardon me?
So the Hilbert scheme is in some way unique.
Well, it depends on the ambient project space and on the Hilbert polynomial. Given Hilbert polynomial and dimensional project space, it is unique, yes. For what scheme? Well, it depends on some projective variety, X, and some coherent sheaf, or maybe just locally free sheaf, vector bundle, and again, the Hilbert polynomial of its quotient. Squat. So it also parameterizes all the quotients.
А что здесь является модулем? Вот вы в прошлый раз говорили, что это является решением проблемы.
Oh, yes.
Что подразумевается под модулями? Вот это
Well, we formulated this problem last time, and we'll formulate it next time. But maybe now let me say it roughly, and not very rigorously. So in the same way, it parameterizes all the possible quotients like this with the Hilbert polynomial of f. And by definition, this is the, well, so to say, this Hilbert, how to say, maybe Hilb, f of r, this is equal to the Euler heuristic of x with coefficients with twisted sheaf.
вот этот объект, он как пространство модуля или нет?
Yes, this the solution of a moduli problem. Yes, certainly. Well, given by H, and here X is embedded into some ambient projective space, and hence it makes sense to consider O X of R. Okay. So if you want to apply this existence theorem to the Hilbert case, just take X equal the ambient space and E equal to OX, and get Hilbert scheme.
Почему так ведь объект схемы, Гильберт, составляет множество подсхем проективного?
No, it does not consist of subschemes. It parameterizes subschemes. Its points are yes.
А здесь как бы два подпучка. Здесь как бы
But I tell you, just take the structure sheaf of the ambient variety, and then take its quotient sheaves, because a subscheme, whatever Z in Pn, it's equivalent to its structure sheaf. Z being the quotient of OPN. Right? And as I stressed last time, for schemes we need the multiplicative structure on the structure sheaf. For quotient sheaves, we don't require any multiplicative structure, but the quotient sheaves of the structure sheaf necessarily inherit this multiplicative structure. Okay, so you don't need to additionally specify it. It's automatic.
Откуда мы U и P берем?
Pardon me?
Откуда мы берем U и P?
Well, it's a theorem we're going to prove. This is a deep, difficult theorem that will take us at least 2 weeks to prove. The existence of this Hilbert's or this quote scheme.
Вот вы говорите, что здесь квот-схема?
Yes. I just say that the Hilbert scheme in this case is just literally the quote scheme of what? Pn, O, Pn, and Hilbert polynomial H.
Я так не понимаю, вот P и U, они относятся к схеме Гильберта?
Well, yes. When I say that there is this quote scheme, it represents some functor. So it means that there is some universal family. Again, over this quote scheme, there is just P n times quote scheme, or maybe X. Sorry, X times this, and there is the pullback of our sheaf E. Okay, and it projects onto some universal sheaf F. I don't know how to say that it's universal. Whatever. Maybe like this. Okay, and then how did I say this? The fibers of F universal are all the quotient sheaves of E with Hilbert polynomial equal to H. Okay, and also this F universal is flat over the quad scheme. Okay, just the same.
Could you once again repeat? So we have a functor which,
Yes.
Which maps sheaves.
So last time I said that there is some functor quad, and it's representable by this thing.
There's a universal family from
Well,
functor is representable, meaning that there exists a certain object, yes, field, which
yes,
or quad.
yes.
And the family is something different. This F union. It is not in the definition of the representable.
It is. Maybe you think about it and you see that it is.
То есть это не такая теоретическая категория.
Well, definition is categorical if you want, of representability. But the construction is very particular. And now we'll start proving the existence. Yes.
Есть какой-то контрпример к существованию такого объекта, когда нельзя построить представимый, ну, чтобы функция был представим?
Well, there is a very well-known example that Daniil knows very good. Yeah. So the famous counter example. So the functor L from schemes to sets associated to a test scheme S, the set of isomorphism classes of flat morphisms whatever X S such that all the fibers are elliptic curves.
Это не тривиальное утверждение, это очевидно.
No, it's not evident at all, but so the solution of this moduli problem would be the moduli space M whatever 1 1. Maybe I need the curves, I mean with 0, so to say. Of yes, elliptic curves was marked point. Just the zero of the group law. Well, it is known that such thing does not exist as a scheme. It is a Mumford stack. So the problem is that some elliptic curves admit more automorphisms than other. Here there are no in the Hilbert problem and in the quad problem there are no automorphisms whatsoever because there is a rigidity like this. Since this thing is fixed, you cannot have any automorphism of the quotient because it's represented as a quotient of something. Like the generators are fixed, and there are no automorphisms. Because of this, there is a chance that it could be representable by a scheme. Otherwise, there would be no chance it would be representable by a stack. Indeed, it is representable by a scheme. So the important thing is the absence of automorphisms.
But Hilbert scheme parameterizes subschemes of projective space.
Yes, and this ambient projective space is the required rigidity.
Suppose this subscheme has automorphism.
No. Once again, it is not an abstract scheme. It is a subscheme of project space, and this ambient project space is fixed. So you do not consider any abstract automorphisms. You consider them as embedded schemes. Yes, not by itself.
If I apply automorphism to my subscheme, this will be two different points in Hilbert scheme.
Yes, because
If you wish. Well, I'm erasing, unfortunately, this definition of quad scheme, but still we have the quotient, like this, and then the very rough idea is to consider the global sections of the ambient of this sheaf, the quotient of global sections of this generating sheaf. So first of all, there is no reason for such a surjectivity, because the global sections are left exact but not right exact. So no reason for this. But if you twist it sufficiently high, then there will be no higher cohomology of the kernel, and there will be such a surjection.
Почему универсальная схема существует или это не универсальность?
Well, we are starting to prove the existence of quad schemes. It's a deep and difficult theorem, and the proof will take us more than 2 weeks. And if we keep repeating this statement more and more often, it will take us 3 weeks and even more.
Мы сейчас доказываем, что она существует, или мы сейчас доказываем что-то другое?
We're starting to prove the existence. I'm formulating the rough idea of the proof.
А почему мы тогда пользуемся, что она существует, если мы еще не доказали?
No, we're not using its existence.
Ну, слева вот мы написали универсальную схему.
I don't see any universal scheme here. So maybe let's stop this discussion and consider such a quotient. And it defines a point in some Grassmannian variety. So it will be, the quotient will have this dimension, and this dimension we know it's h of r inside this space, or quotient of this space. Okay, so we don't know yet what scheme exists, but at least there is a morphism like this. And also there is a morphism like this when you increase h. And so on. This rough, well, the rough idea is that this is the closed embedding. So the quad scheme will be constructed as a closed subscheme in such Grassmannians. And then it's maybe easy to see that indeed it does embed into the product of all these Grassmannians, but it's an infinite product, and that's not what we want. We need some finite product. In fact, in the end, we'll prove that it embeds just into one particular Grassmannian, but for a very big R. Okay, that's what we're aiming at. But it does embed into the infinite product, and we need to prove some finiteness. So now we'll start some technical preparations, and you will see Grassmannians only in 10 days, unfortunately. We'll do some technical preparations, and you will have to take my word for what they are for. Okay?
Once again, the morphism is not well defined for all.
No, it is well defined, but it is not an embedding. Eventually, it will become an embedding. That's the point, and it will be a closed embedding. But it's rather hard to prove this, and we're starting to prove this.
But if F, you need different like twisting to.
To begin, absolutely, right. If we fix one particular F, then it's clear that for some particular R, I don't know even what to say, because if you fix one F, you obtain a point here, and this is just a point. But you want to obtain an embedding from all the possible parameter set of F into one particular Grassmannian. And it at least from the...
Excuse me,
Yes.
I don't understand
Yes.
completely how
Yes.
by the quotient we construct a subspace in the global sections. I think we construct...
No, when I say Grassmannian, I mean this dimensional quotient of this vector space. But it doesn't matter. Take kernel, you will have subspace, it doesn't matter. Okay?
But
Yes.
in shapes you have morphism started for a particular R and so on.
Okay, so we want to find one common R for all the sheaves. That's some boundedness assertion, very strong boundedness assertion, and it will take us at least 3 times to prove it.
So it is not evident.
Absolutely, no. That's the whole content of the proof. Some boundedness. Okay. Okay. So we are starting the proof, but as I say, we will prove quite a few lemmas about general structure of flat sheaves that will eventually imply the required boundedness. But you will see what will happen today. It will have nothing to do with quad schemes, Grassmannians, and anything like this. So we start with a coherent sheaf. So a long preparation. For boundedness. So to say, of all possible quotient sheaves of E. And we start with a coherent sheaf on a projective space. And we take some integer, and there is an useful notion going back to Mumford or whatever, Castelnuova, that F is called M regular if for any positive integer the ith cohomology with coefficients in F twisted by M minus I vanish. Okay, and if you read through your home assignments, I forgot, maybe it's April, whatever, 20 something, I forgot. There is a whole home assignment about regular sheaves, and you'd rather solve it, or at least read it. Okay, I mean not right now, but maybe right after this lecture. Because I will use some properties of regular sheaves that are formulated in the home assignment. I will not prove them now. Okay, and now the base of all boundedness and finiteness results is the following theorem of Mumford. So in particular, Mumford is a student of, well, strictly speaking, he's a student of Zariski, but then Zariski sent him to Grothendieck, and Mumford worked with Grothendieck. So today we'll prove this theorem of Mumford, but as you may imagine, the original proof by Grothendieck was different. So when Grothendieck gave his original proof, Mumford was yet an undergraduate student or whatever. And then later on, in 5 years, he reworked this proof and made it better and shorter. So the statement is rather long. So for all integers, positive integers, there is a polynomial Fpn of n plus 1 variables with integer coefficients. So such that for any sheaf on project space, but such that it's not a quotient C sheaf, but a subsheaf of the trivial structure sheaf, P copies. Okay, so M is dimension of the base of project space, P is the rank of the ambient vector bundle, and we consider all the subsheaves here. Then the Hilbert polynomial chi of f twisted by r is the sum of binomial coefficients. I mean, this is for this is automatic. Yeah, because we know that the Hilbert polynomial has rational coefficients, but integer values, and any such polynomial, numerical or integer polynomial, has this this form. So AIs necessarily are the integers, and for any sheaf like this with Hilbert polynomial like that, f is M regular in that sense for M equal FPN of this n plus 1 tuple of integers. Okay, looks weird, yeah, but we have to start somewhere. I'm sorry.
Why
Yes.
M summons?
Well, you know, F is a coherent sheaf on n-dimensional project space, and then its Hilbert polynomial is of degree n, right? Right?
Yes.
And it's numerical or integer valued, and so it necessarily has this form. There is no statement here. The statement is there. Okay? So I hope you wrote down the statement of the theorem, because I would rather not copy it anymore, but I will have to erase it soon. So I promise you that this is the basic boundedness statement, because it says something good about any sheaf, just knowing the dimension of the base and the ambient rank vector bundle. Okay, so we consider the corresponding quotient sheaf. And we know that there is a hyperplane H in the projective space, such that the first door of this hyperplane structure sheaf and f prime is 0. And this is one of the one of the exercises that I mentioned. And let me comment quickly about this. So f prime might have some torsion, but this torsion may be of various sorts, and it has the worst possible torsion supported points. Okay, so it contains the maximal subsheaf f prime 0 supported at some zero-dimensional subscheme in Pn. So I mean, for curves, it would be just the torsion subsheaf. But for, say, P2, we could have some subsheaf-supported curves, like this. But also, there are some supported points. Also, there is something with full support. Sorry. But we are interested in this zero-dimensional supported sheaf. Okay, and then I claim that this hyperplane must avoid the support of F0. It's just a finite subset, so we can find a hyperplane that avoids this subset, and then necessarily the first Tor with this will be 0. Okay, and that's in your home assignment. And this is difficult. So we know we can find such a hyperplane, and then we will somehow restrict everything to this hyperplane and proceed by induction in dimension n. So we have this short Z sequence. 0 to F to O, P, and P to, well, sorry, this will have mathematically, but from this and the vanishing of Tor, we obtain by restriction to H this, and this quotient. So we see that the restriction of F to this hyperplane lies in.
You always have sticks.
Pardon me?
You just mean that this is an embedding.
Yes, this is an embedding. Yeah, that's what I need. And so we will. It is a similar situation in dimension 1 less, so we will proceed by induction. Okay, so now F had no torsion, because it was subsheaf in the locally free sheaf, and hence we have another short Z sequence. F of -1 goes to F, goes to restriction to the hyperplane. Okay, so in principle, this canonical morphism could have the kernel, but since F has no torsion, there can be no kernel here. Okay, and from this we see that the Euler characteristic of Fh twisted by R is the Euler characteristic of F twisted by R minus the Euler characteristic of F twisted by R minus 1. Okay, and we can write. Yes? Yes.
How you derive the second? The Tor 1
Apply the tensor. We can multiply by all.
Yes. But
we need to tensor.
we just tensor with, we just take this and tensor this whole thing over O, Pn, yeah, with OH. But the tensoring is not exact, but since the store vanishes, this particular thing stays exact.
And since F have no torsion,
Yeah, then we derive this other Z sequence. Yeah?
yes, why F had no torsion?
Yeah, I also have this question.
F has no torsion because it is a subsheaf of the structure sheaf, which I hope you agree has no torsion, right? So any subsheaf has no torsion either. Agreed? So when I twist it, it still has no torsion, and so there could be no kernel here, right? Okay, so we have this difference, and we can rewrite this difference. Once again, this is our assumption, and there's nothing to assume. Yeah, any Hilbert polynomial looks like this. So we just have some AIs, and we will rewrite this formula in terms of AIs. The sum from I equals 0 to n, AI, R choose I, minus the sum AI, R minus 1, choose I, and then it is the sum of AI times R minus 1, choose I minus 1. And this is the sum from j equals 0 and now to n minus 1 of certain bj's r choose j. Okay, and those b1 so on b0 so on b n minus 1 are polynomials. Well, bj equals some polynomial gj of a, some polynomial with integral coefficients independent of f, and if you wish, of a ground field either. Some universal polynomials, they depend on nothing whatsoever. Fine. So by induction assumption, there exists some polynomial f, p, n minus 1 of n variables such that fh is m regular, so let's say m0 regular for m0 equals fp n minus 1 of those b guys, and then we can rewrite it as certain polynomial g of a guys, because b's are functions of a. Pardon me? Base of induction is when we have pp not, so just one point, and then I trust you can prove it without my help. Okay. Okay, so we will need this polynomial g. It's again with integral coefficients, and again doesn't depend on anything at all. Fine, and unfortunately I erased the definition of regularity, so maybe let me write it down here once again. It means that the ith cohomology of Pn, or maybe okay, Ppn with coefficients in f of f minus I is 0. It's M regularity. So now I'm erasing the statement of the theorem. Okay. So we know that fh is M not regular, and it implies that for any M bigger than M naught minus 1, we have the following exact sequences. So I mean, these are the sequences just come from that one, and the only use of this regularity is that they are not infinitely long, but they stop right away. So we go to h1 of f minus 1, then to h1 of f of m, and then it stops abruptly. There are no higher cohomology of this sheaf on the hyperplane, and also for second cohomology there is no cohomology whatsoever. So hi of f minus 1 is isomorphic to hi of f of m for any I greater than 2. And again, if you wish, this is in your home assignment. Some higher cohomology vanishing, it somehow immediately follows from the definition, but it's in your home assignment. Okay, so yes.
Вы уже использовали, что H содержится в OH степени P?
Well, yes, it has no torsion. We use this.
Когда вы точно последовательность писали?
No, we just applied induction assumption, right? So if I just erased the claim, but in this claim you assume that your sheaf F was a subsheaf in the trivial vector bundle, and the same is true for its restriction. And so we can use the induction assumption on the dimension of the base project space. Okay. Okay. So what do we know? We know that if we twist sufficiently with a sufficiently big twist, then there are no higher cohomology. This we proved a long time ago. Okay, and so it implies just by this that the higher cohomology of f of m is 0 for I at least 2 and m at least m0 minus 2. Okay, just because eventually it gets 0. But then there is an isomorphism with previous one, and then with previous one, with previous one, so on. Now, from the surjection H1 of f minus 1 onto H1 of f of m here. Yeah? We see that the dimension of first cohomology decreases monotonously, if you wish. As long as m is m0 minus 2 or bigger. Okay, so it goes down, and eventually it becomes 0. Now, what we are going to prove now is that it decreases strictly. Not that it can behave like this. No, it decreases strictly until it reaches 0 level, and then it is always 0. Okay, so in other words, it vanishes pretty soon. Not that it could indefinitely linger and then eventually vanish. It goes fast to 0, and then it's always 0. That's our next lemma, if you wish. Oops. Okay, so lemma for m bigger than m0, h1 of f of m decreases strictly until it reaches 0. Pardon me? Small h1. Small h1 is the dimension of this. Well, where do I say this? I know. Okay.
And why if you have this surjection, then if you say m goes
Yes?
bigger and bigger, and h1
Smaller and smaller.
yes, why?
Well, we have this surjection. So, well, you see, it's surjection. So, the dimension of this is smaller than the dimension of that. Nothing clever. Yeah?
And
Nothing.
if m, and then m minus 2, if we have,
Then it starts going down.
Once again, okay, I have a question about regularity. So
Yes.
regularity means that the particular cohomology is 0,
Mhm.
but then here you use
For any I. Yes.
I don't understand how it implies this, because
Well, if you solve your home assignment, you will understand. I am absolutely sure about this. Just at least read through your home assignment. You will have this statement there.
I do, but I will do it, but this is not...
It's not yes, it's not absolute. It requires some work, but not a big work. Yes.
Просто чтобы понять.
Yes.
Это априори очевидно, что оно дойдет до нуля?
Yes, absolutely, because we know that we are at least sufficiently high. There is no higher cohomology. That was proved a few months ago.
M увеличивается.
Yes, yes. for very big M, any coherent sheaf at all, absolutely, on a projective variety, if you twist it sufficiently high, then has no higher cohomology. Huh?
Я просто думаю, что мы M уменьшаем.
No. M goes up, but dimension goes down. Okay? Fine. So let's, well, we will prove this in a moment, but it will imply that the first cohomology of the twisted sheaf equals 0 for M bigger than M0 plus the dimension of F of M0. Okay, and that's nice because this can be computed. Well, this is known explicitly by induction assumption, right? This was our induction assumption, and this can be also computed explicitly from the Euler characteristic because there will be no higher cohomology, and you need only H0 and H1, and the Euler characteristic is given by the Hilbert polynomial. So we'll do this, but somehow I just want to say that this lemma is really useful. It's our decisive step towards victory. So, the proof of lemma, we know that H1 of F minus 1 is not less than H1 of F of M, and well, for M at least M0, and the equality here holds true only if, well, if and only if this map here is surjective, right? So if this map is surjective, then this is an isomorphism. So if nu M is iso, okay, no, not iso, but surjective. Is surjective. Well, but we know that FH is M regular. Well, it is M0 regular, but M is bigger than M0, and hence it's M regular. And it's again in your home assignment. So if some sheaf is regular for M, then it will be regular automatically for all the bigger things. And from this, again, by home assignment, it will follow that this map from H0 of F of J to H0 of FH of J, like here, will be surjective for any J bigger than M. Okay? Again, this is proved in your home assignment. It's not a big deal, but you do it at some point. Okay. And so it implies that then H1 of F of J minus 1 is equal to H1 of F of J for any J bigger than M. But we know that for big enough J it is 0. So we are done. Okay. So since H1 of F of something big is 0, we are done. Fine, so lemma is proved. And now we'll apply this observation, corollary of this lemma. And in fact, we are almost done. The theorem is almost proved. Okay, so we must estimate this H1 of f of M0 just from our assumption that f is contained in the trivial vector bundle. Okay, so it means that H0 of f of R is at most P times H0 of O of R. Okay, this we can compute. This is P times n plus R choose R. Yes.
Comment on the previous. Why we are
Yes.
we want to prove that this dimension does decrease strictly.
Yes.
And why it is so?
Because if at some point it stops decreasing, then it will never decrease again. But eventually it must be zero, so it can only stop decreasing at zero.
Why will it never stop decreasing again?
So the equality here only occurs when you have such a surjection. This is always surjective for j bigger than m, right?
But it could be subjective for j less than m too.
No, but we are all sorry. If it so for one, when it is one particular m, and if it is equality, then for all the bigger j's, it will also be an equality. That's what is written here. But if it starts, if it stabilizes at some point, then it's always stable from this point on.
Ah, I see.
So it cannot go like this. Whenever it starts stabilizing, it will also always be stable. But then we know that eventually it's zero, so it must stabilize only at zero. It cannot stabilize before it reaches zero. Okay? So we know the dimension of global sections, just because our sheaf is subsheaf in the trivial one. We know that there is no higher cohomology. H bigger than 1 is 0. If m is at least 0 minus 2. And so from this H1 we are after, right? We want to estimate H1. H1 is just the difference H0. Minus Euler characteristic. Okay, and this can be computed. So this is at most p times n plus m0 choose n minus the altruistic we already know is the sum from I equals 0 to n, ai m0 choose I. Okay, and so this is some polynomial p. Where? No, I think everything is fine. N plus m0 choose n. It doesn't matter. To choose m0 or choose n is the same, right? So it's some polynomial p of a0 and so on, an, where this polynomial p of a is obtained by substitution m0 equals g of a. Yeah, we had this computation before, yeah, at this very place, if you remember. Well, into this formula, just replace g of a in place of m naught. All right, fine. So, in particular, the coefficients of p are independent of our sheaf f and the ground field k. And now we are really done. So we know that h1 of f of m0 is non-negative, hence this polynomial p of a is also non-negative, and just substituting in there we get that well, we had it here half an hour ago, but well, we obtained such an expression. It's some polynomial independent of some universal integral polynomial. Okay, we obtained it some time ago, but we only need to know that there is some universal integral polynomial. Okay. Yeah. From induction assumption, we obtained this. So we know that p is positive, and substituting in this expression, we see that the first cohomology of twisted sheaf is 0 for any m bigger than g of a plus p of a. And finally, this is our desired f p n of a. Okay. Yeah. That's it. Well, here we use it here. This follows from lemma because. Well, just we know that something is good for m well, not absolutely very big, but just bigger than M0 by this particular H1. And then we compute H1. We need to know some cohomology vanishing in some particular degree. So it's this boundedness we'll use for embedding into Grassmannian. We know that if you twist your sheaf sufficiently high, then it will have no higher cohomology. But we don't know some constructive bounds, explicit bounds. How high do you have to twist? And here is an effective bound. You know that, well, this is an explicit effective bound. When you twist just by this, no higher cohomology. That's what we'll use all the time.
Тему конкретную ты используешь. Ну, в конце. Сам концепт.
Yeah. Just here.
How we, let's go back a little.
Yes.
How we derive this bound m bigger than m0 plus h1?
Because we know that this dimension of H1 decreases, and it strictly decreases until it reaches 0. So it was something. Then it became at least 1 less. At the next step for m plus 2, it became at least 2 less. For m plus 3, at least 3 less. Until it goes down to 0. So we know that whenever you make H1 steps, you are down to 0. Or even before this. Okay?
We have a question. We want
Yes.
regularity for all I, but we only proved it for
H1.
H1.
But we had these exact sequences that make sure that then everything else vanishes automatically. Okay. But when you solve your home assignment on regularity, everything will become absolutely clear. Okay, fine. So we're done with this important theorem, and now we start something different, some general study of flat sheaves. And let's prove some lemma. Unfortunately, we'll have no more time. Lemma. Well, maybe it should be numbered 1. And next time we'll have lemma number 2. So we have a scheme S, the base scheme S, and we have a projective space over this scheme with projection pi S, and then we have some other scheme with a morphism phi to S, and then we also have projective space over this guy, so it's pi t, and we have such a Cartesian square. And we have a coherent sheaf on the projective space over S. And then I claim that there exists a twist sufficiently high such that there's a base change in this diagram. So the canonical morphism from push, pull, pull, push to push, pull is an isomorphism for any r bigger than r0.
Here it depends on.
Pardon me?
Here it does depend on that.
Yes. Depending. It's not a universal constant. It depends on f.
Можно пару глупых вопросов?
Yes.
Во-первых, что такое проективная плоскость? Ну, пространство. S?
Well, if you are working over ground field K, then Pns is just the product of Pn over K times S over, well, spec K. But then it doesn't really matter. It works over arbitrary base scheme. Just take projective spectrum of polynomial ring over this S, whatever. The usual construction of project space works over any ground ring, and so it can be glued over any scheme. For example, over integers.
Квадрат он просто коммутативный или...
It's a Cartesian square, so this is the Cartesian product of those two over S, and that's again evident just because the projective space is given by some universal construction. If you wish, it exists over spectrum of integers, and then you can pull it back to any scheme that projects to the spectrum of integers.
Я видел, что здесь просто обозначение реактивного пространства, а справа пишут кольцо А, в котором все определено.
Yeah, you can also use this notation. Well, I don't know. I think we understand what we're talking about. Yeah. There's no reason to go into deep study of various different notations. So the proof is also due to Mumford and very elegant. It is the localization of coherent sheaves on project space. Yeah, you probably remember that over an affine variety or an affine scheme, coherent sheaves correspond bijectively to finitely generated models over the ring of global regular functions. And something similar holds for projective space, but there you get graded modules, like sheaf F goes to the direct sum over all R global sections of projective space with coefficients in the twisted thing, and this is M. And this way you obtain Serre equivalence between coherent sheaves on Pn, say A, as Daniel suggests, graded modules. Over A. So they are Z-graded, vanishing in degrees very negative, and take a modular finitely generated modules, A modules. Okay, again, we discussed this maybe last December, something like this, I hope. So our sheaf F corresponds to some graded module M. Okay, so maybe instead of taking global sections, global sections make sense maybe really over some ground ring, but over ground scheme I should rather say not this, but pi s lower star F over. Okay. Yes.
On the left hand side, we have F, which is the right, it is a sheaf.
Right.
PS.
Right, absolutely.
We apply P upper star to it. Phi upper star.
Yes. Yes.
To apply phi upper star, we need a sheaf on S.
No, phi is upper, upper.
But we need phi upper and lower.
I think it's clear what is written here, but if you insist, absolutely, I can write P here. Yeah. But I think it's better the way it used to be. Huh? So, our sheaf corresponds to such a graded sheaf, graded coherent sheaf over S. Fine. And then F is the localization of this graded module. And its pullback is the localization well, how to say, I can pull back our module M dot and localize it. Okay? Okay? Yes.
Is S phi?
No. S is not an arbitrary scheme. But the question is local, and well, we can choose something on the affine patches. It doesn't matter. Here I never assume that S is affine. I just take the push forward.
But if you like speaking, say that these two factors are the same, I think you have to assume that S is affine, and then it is this.
Once again, if S is affine, then it makes sense to speak about this, and it is nothing but that. But in general, you don't have this, but you can only speak of this, that. Fine. So we computed the right-hand side, in a sense. And now set n dot is the direct sum, over all integers over pi t push forward ft of r. Ft is the pullback of f.
Here the localization works along the fibers of this module.
Localization works for projective schemes or arbitrary basis. Yeah, that's what we use. You can do it over rings, and then you can glue it for the affine cover of arbitrary base scheme.
For me, this is an NU idea.
In you, but very fruitful idea. Yeah. Okay, so we can take this n, and then with this definition, the pullback of f will be just the localization of this graded module n. Okay, and now we see that the same localization is obtained from two modules. Okay, so it's equal to that, but also it is equal to the localization of the pullback of M. Okay, and it implies that those two differ modulus and finally generated module. In particular, they are the same in all the very high degrees. Well, M, whatever, M is this for M very big. And that's what we needed to prove.
What is FT?
FT is the pullback. Phi is here. Yeah, so we have a sheaf F here, we pull it back, we obtain the sheaf FT here.
It's just the phi upper star and dots tilde.
What's your question again?
Is it just the localization of the phi upper star of n dots?
This is the definition. And it's also a localization of this.
Is the localization the same as take a pullback of a shift under this projection?
What do you mean by this? Well, when I say localization, I mean this equivalence due to Serre, yeah, between coherent sheaves and Z-graded modules. So when I pass from Z-graded module to coherent sheaf, that's the process of localization.
If we have sheaf on the projective space and we push forward the localization.
Well, we push forward all its twists, and we obtain some graded module. Well,
The sum of push forward of space is the module which.
so in one direction, it's like this. In the opposite direction, it needs some construction. We discussed last December. You will have some localization. You will pick something of degree 0, and then you will glue over various affine charts.
Also, I have a question. Do we have module of finely generated A modules or?
Yes, finely generated A modules, yes. And what else could you say? There are no alternatives, right? What other models can you consider? Just finely generated. In case of ground field, it will be finite dimensional. Yeah. So I think that's it for today. Thank you. But I urge you to read through this home assignment, though it is due only towards May.